All right. Hey, everyone. I'm going to talk about some joint work I did with my advisor, Igor Pak, on stretched or scaled Schubert coefficients and their eventual quasi-polynomiality. So for some quick motivation, just define stretch partition. You just scale each entry component-wise by some natural number, some positive natural number. And then there's a theorem shown by Dirksen Wyman and started independently that if you look at the Little Richardson coefficients of these scaled partitions, and then you think of this as a function in terms of n, this is in fact a polynomial in n. So it showed a while ago, and it was our goal to generalize this to permutations. And by generalized, I mean when we look at Grassmannian permutations, which have like a corresponding partition, that we recover this. So first we need to define what a stretched permutation is, right? We want to define something such that with a stretched permutation, specifically if we stretch a Grassmannian permutation, it corresponds to the same like stretching of partitions. And so to do that, we're just going to scale the lemma code. And the lemma code is defined as this like tuple of natural numbers, where the ith entry is the number of j that are larger than I, where w of j is less than w of I. And then we scale this lemma code just by like the natural number, and then we can like take this like code inverse function. I think it's best described by an example if you haven't seen this before. If w is 4132, the code is 3010 because 4 is bigger than the remaining 3 numbers, 1 is greater than neither of them, 3 is greater than 2. And then you multiply this by 2, and then you get an element of Sn, as you can see. So, so generalizing this, we're going to be looking at the Schubert coefficients of these stretch permutations. So first of all, Schubert coefficients, I'll do a quick overview. It's going to be a little bit different how other people have talked about it today. We're going to talk about them in terms of pipe dreams. I'm not going to give you a definition, but here's an example of a pipe dream. The crosses represent where the two pipes cross. Dots represent where they sort of bounce off each other with these like dual elbow tiles. I'm only ever going to be talking about reduced pipe dreams, so they can only cross once. If I ever just say pipe dreams, I'm thinking of reduced pipe dreams. And we're also going to have this distinguished bottom pipe dream, which is like drawn over here on the right. And the reason distinguished will come up later, but it's just going to have the code number of cross tiles in row I left aligned. And you can check with me for this example. This is indeed a pipe dream, but it's always going to be a pipe dream, and it's the minimal one in terms of some sort of order. So Schubert polynomials, the way that we're going to think of them is as this sum over pipe dreams of x to like the weight of the pipe dream, where the weight is just the number of cross tiles in row I. It's this tuple, which is the number of cross tiles in row I. And then Schubert coefficients, we're going to think of them as these like the structure constants that happen when we decompose in terms of this basis, as we've seen before. So our main result, now that we have sort of all the notation, is that while this might not be just a polynomial, it is eventually a quasi-polynomial. So what does this exactly mean? It means that for large enough n, there are some like finite number of polynomials, g0 through gn minus 1, such that this function agrees with gi of n for when n is congruent to I by n, right? So it's not just a polynomial, but after some period of time, it becomes like a set of polynomials that on residue classes. And actually, so another piece of motivation for this is that this immediately resolves Kirilov's conjecture from 2004, which is that the corresponding generating function is a rational function. Kirilov also conjectured that these are actually polynomials. We weren't able to prove that, but it still satisfies that this is a rational function. So I have enough time to hopefully go through a quick sketch of the proof. So the Schubert Koska numbers are just like the Koska numbers, except for Schubert polynomials. It's the coefficient of some composition A in the Schubert polynomial for W. But we should really be thinking of this as the number of pipe dreams for W with weight A, right? Because the Schubert polynomial is just the sum over pipe dreams of x to the weight. And okay, this lemma looks a little bit confusing. Actually, it was brought up in the very first lecture today, in the very first talk today. But the important thing we should look at is that we have this sort of this signed sum here. This sum over here ends up just being the number of triples of pipe dreams with a certain sum of weights. So this like omega of sigma says that we have our A plus B plus C equals to this thing. So we're saying how many pipe dreams are there for U that have weight A, pipe dreams for V that have weight B, pipe dreams for this like sort of flipped W that have weight C, such that it adds up to this thing. So we're going to take this sum that's over some finite thing in terms of capital N of these like number of triples of pipe dreams, right? So for our purposes, it suffices then to show that this thing, the number of triples of pipe dreams, is eventually a quasi-polynomial in our scaling factor. So how are we going to go about that? So we're just going to be counting triples of pipe dreams with a certain sum of weights. So to do that, I'm going to introduce ladder moves. which is a way to turn one pi prime for a permutation into another pi prime for that permutation. We're going to move this plus here up to here. And this m can be 0, so we could think of just moving like the plus up and to the right 1 if these three were dots to begin with. And we also have inverse ladder moves defined similarly. The reason these are important is because it's a theorem of Bergeron and Billy that we can actually obtain any pi prime for W from this like distinguished model. So it's minimal in this like order, and we can just sort of like go up this order by doing ladder moves to get any other pi prime. Conversely, given any pi prime, we can move things down by doing inverse ladder moves until we get to the bottom. And basically, the main idea of our proof is to find some way to encode how we get from a pi prime by doing inverse ladder moves down to the bottom one, and encode this as just like a sequence of numbers that is like will behave nicely when we scale, when we do this like stretching of the permutations. So I'm not going to define a compatible ladder sequence, but I'll let you stare at this example for a little bit. So basically what this algorithm is going to do is going to take the bottommost, rightmost set of pluses that are not left aligned. Nearby set of crosses, I mean like ones that are not separated by dots. And we're going to do inverse ladder moves until they get left aligned. So in this first step, we do 2 inverse ladder moves, but we should think of it as moving them sort of like at the same time until they're left aligned. So the 2 red pluses are now left aligned. And then in the next step, we're taking the next like lowest, rightmost plus that's not left aligned and moving it down. Here we did a ladder move that sort of like skipped over a row. And then we did this like green one here. This green one actually moved down in 2 steps. And then lastly, we did this pink one. And we ended up with the bottom pipe prime. And so this encoding is sort of saying we had 0 things that moved in some way that isn't even like shown in this diagram. But whatever, there are 2 things that moved in the red fashion, 1 in the blue fashion, and so on. Right? So we're just encoding this as the number of like pluses that moved in a certain way, something like this. And so being compatible ladder sequence is basically just some system of inequalities that say like the pluses can't like move past each other in an illegal way that is not a legitimate inverse ladder move. So here's sort of like once we have this encoding, again, as I just said, these compatible ladder sequences are determined by just some large number of technical inequalities. The sum of weights condition, you can see how we can recover the number of crosses in a certain row by like the number of crosses that moved into that row minus the number of crosses that left that row plus the number of crosses that started there. So that those equalities actually end up just being also inequalities. And we combine all of these for our triples to say that counting the triples corresponds, counting the triples essentially corresponds to counting the integer points in like a collection, a large collection of polytopes. But importantly, that collection does not depend on our scaling factor. And that scaling factor roughly corresponds to dilation. The roughly here is very important because that's what causes this to be eventual and not just like a quasi-polynomial from the get-go. So I have 20 seconds left, so I'll just flash up these examples. The reason that these 2 examples are pretty interesting is because together they contradict both directions of the saturation conjecture, which is something that is true for partitions. This example shows that the coefficients need not be positive, which was also conjectured to be true. And this example shows that while it can be non-zero to begin with, it can be 0 everywhere afterwards. So we do need this like eventual condition. Thanks.
We have time for one question.
Yeah. You say like almost violation.
Yes.
What is almost
So
violation?
So basically, there's like some offset. It's like your polytope isn't maybe like centered at the origin. It's like translated a bit, but then you're scaling it, and it's still offset by the same amount. That offset doesn't get scaled with the rest of it. But then it ends up being like eventually polynomial once the scaling is large enough. The scaling is the only thing that's important. The offset becomes irrelevant.
Right. Let's not say again.